Thank you, and thank you for the invitation. So I'm going to tell you about a workflow for low-power neuromorphic computing for event-based vision. Our group is just getting started with event-based vision, but you'll get a feel for the sorts of things that we're most interested in and what we want to apply event-based vision for within those constructs over the course of the presentation. So I am part of a much larger neuromorphic effort at the University of Tennessee. We're the TENNLab Neuromorphic Computing Research Group, and as you all could tell from Kaushik's talk, or if you were in the neuromorphic community, we're reinventing everything in the neuromorphic computing stack, top to bottom, across the field, and we have all of those components at Tennessee that we're working on simultaneously. So we're really interested in doing application, algorithm, hardware, co-design, so all across the stack with the folks who are part of our research group. So I definitely want to acknowledge them. This work is definitely not mine alone. It's a lot of different people have contributed. And if you're interested in learning more about what our group does, you can visit our website. So one of the big things that we focus on is two of the leads of our group, me and Jim Plank, are computer scientists. So we are coming at neuromorphic computing from a computer science perspective. I'm more of a machine learning person. Jim absolutely hates machine learning. So we are a good pairing. He does more of our system software and actually makes what all we do in our group work. So to do our neuromorphic computing research, we've developed our TENNLab neuromorphic software framework, where the core of that framework implements APIs that allow users to interact with neuromorphic hardware and with algorithms and applications. And part of that software core is that common interface, the API that we define, but we also include input and output coding, so if you have problems that aren't natively event or spike-based, that will translate that data into spikes, and output coding that will take spikes coming out of a network and turn it back into decisions or actions or whatever you need for your application. And we also have network compilation tools that allow you to compose different networks. Now, why do we do this? It's because there's a ton of different work in neuromorphic computing that is largely disconnected from each other. So we have this core to allow us to connect different hardware implementations, both those that we're developing at the University of Tennessee. We do a lot of memristive-based neuromorphic implementations. We also look at some spintronic-based neuromorphic implementations, as well as fully digital CMOS hardware. But we also work with collaborators who are developing neuromorphic systems made out of some standard materials, including an architecture that was developed at Oak Ridge National Lab that's currently implemented on an FPGA, so a fully digital neuromorphic system called Caspian, but also people who are making neuromorphic systems out of like biomimetic materials and superconducting optoelectronics. Very different behaviors, very different ways that those implementations actually run and what applications they would be good for. But we have a common API so that I don't have to care about how those hardware implementations are different. I can interact with them from the computer science level without changing my code. And we also integrate with a bunch of external simulators through our software so we can evaluate on aspects that we don't have implemented in physical hardware. Now, we're up to the region that I live in on this chart. So we also implement a wide variety of different algorithms that are compatible with our TENNLab software framework, and we're always interested in integrating more. We have a couple of evolutionary-based approaches, which I'll talk more about in a moment. We have currently one backpropagation-based approach, although we're working on implementing additional. Whetstone is a technique that was developed by researchers at Sandia National Labs. We have a supervised STDP implementation. We have a neuromorphic decision tree and random forest implementation, and we do reservoir computing as well. And then we have a bunch of different applications on top of the algorithm space. And so the goal with our framework is for us to be able to plug and play, to make this modular, so that you as a researcher can come in at any level of the stack and use whichever hardware platform you want to use. If you're developing an algorithm, or if you're an application developer and you do not want to have to worry about algorithms or hardware, you can plug right into that level as well. So I'm going to focus on one of our algorithms. This is one that I developed starting during my dissertation research, so we've been working on it for over a decade, which is an evolutionary optimization-based approach. Now, Kaushik mentioned this morning that it's not always easy to train spiking neural networks to do tasks for you. So we took an approach to target designing sparse, recurrent, and usually pretty small spiking neural networks for real-world neuromorphic applications. And this is an evolutionary-based approach where we assume that somebody has given us a hardware implementation. I don't care what that hardware implementation is as long as it has neurons and synapses on it. And they have a problem that they want us to solve. And they come to us with that combo hardware and application. And what EONS will do is it will attempt to design a spiking neural network for the hardware platform to solve that problem. So the way that it works is we assume we have no idea what the network to solve that problem should look like, and frequently we have no idea what the network should look like to solve that problem. So we start with a bunch of randomly initialized network solutions, different numbers of neurons, different levels of connectivity, different parameters. And then we evaluate and rank them. So if you happen to have an actual physical hardware implementation, you can use hardware in the loop here, load the networks onto the hardware, run them on an application. We're usually doing a simulation of both the hardware and the application here to get a score for how well all of these networks are performing, which allows us to do selection to preferentially select better performing individuals to serve as parents while still maintaining diversity. And then we do reproduction operations to produce children. Our reproduction operations do random mutations. They do crossover, which takes two parents and recombines them to produce children that inherit characteristics from both of those parents. And then we repeat this process. So we use EONS a lot for a lot of different reasons. We use it because it works across all sorts of different hardware platforms. It doesn't care how your neuron works or how your synapse works. It will attempt to operate within whatever characteristics and constraints you have. It will work across a bunch of different application domains. You just need a score to tell how well your network is doing on that application. And you can combine it with different training and learning approaches as well. Perhaps you just want to use EONS to learn the structure of the network and use something else to learn the parameters. There are two major problems with EONS. One I'm going to mention now. It can be slow to converge, but you can make it go faster if you happen to have more compute resources or if you are actually using hardware in the loop. And the second one I'm going to come back to in a moment. So I wanted to give you an idea of the types of problems that we go after in our group. Our group really focuses on control applications because we see that that's an important space where Neuromorphic can make a contribution, where you want to have real-time interaction with the environment, where you need something that's extremely low power. And this is a place where we think Neuromorphic can really contribute. So we always start with toys, y'all, because that's like the easiest place to start. And I will note that this entire project that I'm about to tell you about was led by 2 high school students. So we also start small so that we can integrate it up to higher levels. So this is an example of the sort of project we do. Small scale autonomous vehicle control, particularly autonomous race car control. So this is literally a 1/10 scale car. We did not develop the specification of the car. That came from a community called the F1/10 community. Everything you see in this picture is to spec for that F1/10 build, except for the FPGA-based neuromorphic system, the microcaspian that's zip-tied to the top of the car, as you do in real science. That's not normal for the F1/10 community. Neuromorphic is not usually part of the story here. But this we thought was a good opportunity to showcase what Neuromorphic could actually provide. So what do we do for these sorts of applications? We, for our control applications, typically train in simulation. That F1/10 community provided a simulation environment. Our sensing platform here is LiDAR, the LiDAR that's sitting on top of the car. And we needed a spiking neural network that would take the LiDAR information as input and make decisions about the control of the car, the steering angle and the speed. We train in simulation and then we deploy to the actual physical environments. And that deployment step is always really important to what we do because we're thinking about deployment, we're thinking about what the constraints are of the hardware that we're deploying to, what are the needs of the application in terms of latency. Those are important components. The deployment piece is critical to what we're doing. So this is what the simulated environment looks like on the right of the slide here. And one example of an EONS network that was evolved for this task is shown on the left, and this is a video which hopefully y'all are going to be able to see play. One thing I want you to notice about the network, and this network is controlling the car, which you probably can't see. There is a purple dot that's driving around the simulator there. That's not your eye just like glitching or anything. There is a little purple car driving around there. But what I want you to notice really is the network. This network is very small. we're talking about under 100 neurons, actually under 200 synapses. So very, very small, sparse, highly recurrent. Inputs to inputs connected to each other, outputs to outputs connected to each other. The top row are our inputs, the bottom row are our outputs. And then we have that one lone hidden neuron that it needed for processing, but it's in there, just because it needed it. These are the types of networks that we are targeting. Very small, very sparse, very, very recurrent to solve tasks like this one, driving the car around the track. This is how it actually translates. The network that we train in the simulated environment actually running physically on the hardware that, again, is zip tied to the top of the car there, driving around the track. And I will note, one of the things I'm proudest of about this, we've built this whole workflow to make this easy for people who are unfamiliar with Neuromorphic to step in and start using it. This was a project that was led by high school students, 2 high school seniors, both of whom are now freshmen at MIT, so not like normal high school students, but high school students nonetheless. So I want you to remember that. So we love to do physical demonstrations of the work that we're doing because it provides those constraints that we're trying to operate within. So we wanted to bring that to event-based processing as well. And this is still in progress, but I'll tell you where we're at by the end of the talk. So we have seen EONS do well across a wide variety of different control tasks. That car was just one of them. We've done a lot of things in robotics. We've done a lot of things in other real-world applications, including real-time fuel injection control and internal combustion engines. We've seen that it can produce very small, sparse recurrent neural networks. Here's the second issue about EONS. It doesn't work well when you have very large input spaces. So, in order to apply EONS to applications like event-based processing, we need some way to reduce the size of the observation. So, one of our very smart PhD students, Charlie Rizzo, whose picture is up in the top of the slide here, has developed a way to do downsampling in a neuromorphic way. So, we're keeping everything on the neuromorphic chip. We're going straight from events into a neuromorphic chip that is going to do the downsampling for us, that is then going to go into a network that EONS is going to train to solve a particular task. So this approach Charlie is calling spiking threshold pooling. It works a lot in terms of the high level and the parameters that you're thinking about, as pooling does in traditional artificial neural networks. We have a chip that's defined by its size and its stride, and of course it strides across the field of view. And if you have an overlap at the end, we pad it with zeros if it goes outside the region. Here is a stride of 5, so of course then we do have overlapping chips. And then we have another parameter here, which is our threshold. And that threshold tells us how many events within that chip do we need to actually consider that region to fire as a region. So in this case, the threshold is 3. We're considering both positive and negative polarity events as events here, but you could pick or choose one or the other, and the same sort of approach would apply. In this case, with a threshold of 3, of these 8 different chips, just 0, 5, and 7 would fire. Now, in order to actually do this, because remember, we're always thinking about the hardware that we're going to deploy to. We know we want to do all of this pre-processing neuromorphically. We have to implement this on a neuromorphic hardware implementation. And we're starting with one implementation that we are developing at the University of Tennessee, but this can work across a bunch of different hardware implementations. The networks might look slightly different depending on the hardware characteristics, but the Ravens model is the one we're using here. It has an integrate and fire neuron model with leak, so leaky, integrate, and fire, although that leak is programmable. We have programmable SCDP. We're not using that in this implementation, and we have a novel refractory period. So the way the leak works, you can set that per neuron in the hardware. It's linear leak, so very simple, subtracted from the neuron's potential at each cycle. The refractory period is inspired by biological neurons' refractory periods and is programmable as well at the neuron level, and has both absolute and relative refractory periods. So the absolute refractory period, it cannot accumulate any charge or change the potential during the absolute refractory period, which is the key feature that we're going to leverage here. So Charlie has developed what he's calling counting networks. These are hand-tooled spiking neural networks that you can deploy to neuromorphic systems that will do this neuromorphic downsampling. So in this case, The networks are defined by the rows, the columns, and the threshold in the chipping methodology. And we also have an additional parameter, which is the time coalescing value. It's called F because it's almost turning them into frames, but we're not losing the timing resolution when we then feed them into networks. We have three kinds of counting networks: a general counting network, a pixel counting network, and an optimized network. This is what they actually look like. Were you expecting to see a low-level details of a spiking neural network in this? Get ready, here we go. Okay, so we have input neurons, they're in green. Our output neuron is in red. Here, hidden neuron shown in blue. And we have two different types of synapses. One is excitatory, one is inhibitory, and they have two different synaptic delay values associated with them. We also have our output neuron having an absolute refractory period. So this is an example of a 3x3 region that we would be looking at. And here's an example of how this network would actually work. Suppose the three leftmost inputs are firing. We have an event at each of those at a particular time 0, and it generates spikes on the outgoing synapses for each of those input neurons. The output neuron at time 1 is going to get those three values, those three incoming spikes, which meets its threshold. That's going to cause it to fire, and Raven's meeting the threshold causes it to fire. And then that neuron is going to enter its refractory period, which means that it's going to ignore all of the inhibitory spikes that are coming into it. This is only important because this is saying, okay, 3 spikes happened, I'm firing, I'm ignoring everything else that hits me during my absolute refractory period. This network is now ready to be used again on a new region. If you don't happen to have 3 that fire at any one time, so let's say we have 2 here, this is where those inhibitory connections come in, because the potential in that output neuron is going to be 2. We still have 2 spikes that are coming in that are inhibitory. Those are going to hit and cause that neuron's potential to go back to 0, and now the network is ready to be used again. So this can be used in a streaming fashion as long as you are have your neuromorphic system running fast enough that it can collect data in that streaming way. Very similar to the counting network is our pixel counting network, where it's just going to look to see how many of the individual pixels are actually firing, not how many events are happening. The only thing that's different here is that input neurons, once they fire, enter a refractory period during which they can't receive anything else. So it's just counting how many of the individual pixels actually fire. There's also a version of our network that's optimized for fewer neurons. In this case, we're leaking out the charge on the output neuron so that we don't have to have those inhibitory connections that are going in to reset the potential to 0. Now, why do y'all care? Why do we go through all this stuff? You remember at the beginning when I mentioned that Jim Plank hates machine learning? He likes building networks like these that do something that are useful to machine learning, but that he understands exactly what's happening in the network that he has hand-tooled. So I will skip the examples here and go straight in. So we wanted to start, again, we like to start with toy examples. Now, there's not a lot out in the world, and correct me if I'm wrong. If there is, please tell me, because we would like to know. There's not a lot of simulation control environments that give you event-based sensing data back through them. Carla, one of the autonomous driving simulators, that one does, but that was too advanced for us to start with. We want to start small. So Charlie, same PhD student who developed the downsampling technique, last summer developed a wrapper for the Atari 2600 games. There's a simulation environment, the arcade learning environment. He built a wrapper for that converts the frames of the various Atari games into events. This was a good place for us to start in testing these different approaches and to do real-time control using event-based sensing. So we did a case study where we applied this to Pong, and the screen here for Pong is 33,600 pixels. We use the ALE, Arcade Learning Environment, EBC library that Charlie developed to represent the game screens as collections of events. There's a paper on this, and the GitHub is freely available, so please check that out if you want to play with it. Turns those into events. We actually cropped the screen to only include the necessary pieces. We cropped off the player paddle and the scores, but you could easily leave those in and it wouldn't change the performance of the system. Now we can apply the event counting network as our spiking threshold pooling layer. Our initial pass does a 10 by 10 coalescing just over 1, so not really doing time coalescing at all, threshold of 8 and a stride of 5, and you can see the regions that are picking up there of those different events. This takes us from a 180 by 140 down to a 36 by 28 input space. That's actually still pretty big for EONS, so we do another pass, which is the blue squares that you're seeing that are picking up on, it's actually looking at the green regions, just the spikes that are coming out of the green, and that is telling us where things are happening within the screen. So we are using this to do downsampling. You can also use this to define regions of interest on your problem and help get rid of some of the noise in your background. So this gets us down to an 8 by 6. This is 48 inputs that is now much more feasible for EONS to deal with. Remember, again, hairball of a network that EONS produces, very sparse, highly recurrent. This is the very sparse, highly recurrent network that takes those 48 inputs after downsampling and actually plays Pong. So we have the 48 inputs, no hidden in this case, lots of recurrence, and we just have the two outputs up and down on the paddle. This was the network that EONS trained to play Pong. In this case, what's happening here is it's taking the frames, making them into events, doing the downsampling, then passing them through that network. And remember that all of the downsampling is happening neuromorphically. So it's taking straight the events from your camera. You could feed those directly into your neuromorphic implementation that would do all of the pre-processing for you and then actually come up with the control task. So, to give you a quick summary of what we've been looking at here, we are training spiking neural networks with EONS on simulated events using this spiking threshold pooling to do our downsampling, and we have shown that you can implement this entirely on the neuromorphic implementation, and we have actually evaluated this on hardware on a single monolithic network. Some of the ongoing work, we currently have a set of undergraduate students, because undergraduate students love video games, doing this on a bunch of different Atari games. And we're using the provided method by the ALE environment for episodic stochasticity. We are also using time multiplexing to reduce the size of the downsampling layers in our physical hardware implementation so we can use smaller neuromorphic hardware to actually do this. And we are also actively using this approach to apply to other event-based camera datasets and problems, including a paper at the upcoming ICONS conference on the application of this approach to the gesture dataset that was also showed earlier. On the whole, what I want y'all to take away from this is that we're really working to develop a complete software framework that allows people to come in and do neuromorphic computing, even if they only have expertise in one of the areas of the stack, and to do it on real-world applications, although we always start with those toy applications. We've implemented this neuromorphic downsampling approach, which allows for orders of magnitude reduction in the observation space, and we've successfully applied it across a couple of different event-based camera applications. If you want to hear more about that gesture application using our downsampling approach, or just want to engage with other components of the neuromorphic community, I'm shamelessly plugging the ICONS conference because I'm the general chair. It's August 1st to the 3rd, Santa Fe, New Mexico. You can check out our website for more information on that. With that, I will thank our collaborators and our funding and give you a hint as to what we're working on, hopefully by ICONS. I don't know if you can see the camera pointed at the TV with the Atari on the space here, but we're working on the actual physical demonstration with the camera, the neuromorphic hardware, and the Atari being played directly by the neuromorphic system. So that's it. If you have questions, I'm happy to take them. Thank you.